Hello. Today in this presentation, we're going to walk through the proof of the recursion theorem, um, as well as a couple of its applications. So the recursion theorem essentially states that any Turing machine can be modified to obtain its own self-reference or description. And in order to prove this, we're first going to need to look at how to construct self, which is a Turing machine that simply returns its own description and halts. Then we're going to extend the definition of self to work for any Turing machine. So these are a couple important intermediaries we're going to use in today's proof. So we have the function q, which takes in an input string w and outputs a Turing machine that prints w and halts. And p of w is the notation for the output of q. So if we have p of w, it means it's a Turing machine that prints the string w onto the tape and halts. So now let's look at the description of q. So the following Turing machine, which is quite simple, can compute the function q. We first take in the input string w, and then we construct the Turing machine p of w, which starts off erasing the input, writing w onto the tape and halting, and then onto the tape we write the encoding of p of w. So now let's see how we can use this to build self, which is the Turing machine that can replicate itself. The basic idea is to have these two parts, A and B, where the goal is to output the encoding of both of the parts onto the tape and halt. So intuitively, we can see that our helper function applies, and we can assign part A to be Q of B. So when part A runs, it'll go ahead and print out the encoding of part B onto the tape. Now, the obvious thing to do might be to have part B defined as Q of A. So when part B runs, it'll print out the encoding of A onto the tape and halt, and then we'll have the complete description of the machine onto the tape. However, since we've already defined part A in terms of part B, we can't define part B in terms of part A because that would make the definition circular, which is impossible to actually construct. So we go with a slightly different approach where we have part A as the same thing, so it's defined as Q of B, but we modify part B to be a bit more generic. So part B will take in, it'll read its input from the tape, and it'll compute Q of whatever's on the tape. So it'll compute a machine to print out what it reads from the tape. So in this case, it's going to read its own description from the tape, which was output from part A, and then compute a machine that would print out the description. So that's effectively just computing the value of A from what it's reading on the tape. So now part B has knowledge of both its own encoding as well as the encoding of A, which it was just able to calculate in step one. So it can combine these two encodings to make the complete Turing machine, and then it's going to print out that description of itself and halt. So now we have successfully defined a Turing machine that is able to self-replicate. The issue is it's only capable of reproducing, so it doesn't actually perform any computations on the input it's given. So we're going to use a similar construction later to prove the theorem with a slight modification. So now let's go ahead and take a look at the actual definition of the recursion theorem. So this is a bit technical. It's saying that if we have a function t, which takes in a description of a Turing machine as well as an input string w, then the recursion theorem states that there must exist another Turing machine that can compute the same thing, without needing to take in the encoding as input. So any Turing machine can obtain its own description and go on to compute with it without explicitly needing the description. So again, if we have a Turing machine that needs its own description as input, the theorem gives us an equivalent Turing machine R that does not need its own description as input. So let's now look at how we can modify our proof for self into the proof for the recursion theorem. So similar to the first step, we assign A to be Q of the string W followed by the encoding of the other half of the machine, so BT. So it's going to print out the input string followed by the encoding of B and T onto the tape, and then it's going to pass control to part B. So now when part B runs, it's going to read the tape, apply Q to the contents, so apply Q to W followed by BT, and it's going to calculate A. So now we have WBT written on the tape, and we have A computed by the machine, and then B can go ahead and combine WBT with A to form the complete encoding of itself, which is R, so the encoding of this entire machine, and it will also have the input string W onto the tape, and then we go ahead and pass control to T. So now T can compute whatever it originally intended to, and it has access to the self encoding as well as the input string. So now let's look at the implications. This means that any Turing machine can perform operations that require access to their descriptions without explicitly being passed a description as input. So you can define a Turing machine that counts the number of states it has, checks to see if the accept state is reachable from some state, or even simulate itself on itself, and various other things that require this knowledge of the description. So now let's look at an application of this to prove that the language ATM is undecidable in a much simpler way. If you recall in the textbook, the original proof was using diagonalization, but we can also prove this using the recursion theorem. So let's start off assuming, for the sake of contradiction, that H is a Turing machine that will serve as a decider for this language. Now we'll go ahead and construct a Turing machine B that takes in an input string W. So B will start off using the recursion theorem to get a hold of its own description. And then we're going to run the decider H on the input with the encoding of B as well as the input string W. So we're using the decider to predict what B is going to do on input W. And then as step 3, we're going to do the opposite. So whatever the decider says, we're going to do the opposite. So if the decider says B is going to accept W, then we'll reject it. If the decider says it's going to reject W, then we will accept it. So as you can see, since B does the opposite of what H decides it does, then we've reached a contradiction, and H can't decide ATM. So that's a much simpler proof than the one using diagonalization, using the recursion theorem. And another cool application that's a bit more practical are quines. So these are programs that self-replicate. So it's a program that will run and print out its own source code or copy it to another file. And a lot of computer viruses also use the same construction that we described earlier when we were describing self. So if you look at this one line of Python code, we can kind of see how it's split up into part A and part B, though it's not as clear since we're also doing some logic in the string formatting characters here. But the way this works is we start off by running part A, which is going to output the value of part B, which is the sort of the encoding that's stored in the string, into this variable. and then we pass control to part B, which is the second statement. Part B is then going to read the value in S and combine it using this templating operator, as well as this %r is a sort of raw string formatting, which will reconstruct the part A here. So it's sort of doing the multiple steps in one line, but it'll calculate part A and combine it in this one statement here and then print it out to the command line. So this program will reproduce itself.